Hello everyone. In the last video, we had spoken about the functional group isomerism. In this video, we'll be speaking about metamerism and tautomerism. So let's start first with metamerism. What is metamerism? This metamerism is related to, first we'll be writing here, what is this metamerism is actually related to the polyvalent functional groups. So we'll write the definition here. The isomers which show different properties due to presence of different alkyl groups attached to the polyvalent functional groups is called metamerism. The different properties. So the difference in properties shown by isomers due to presence of different alkyl groups attached to polyvalent functional groups is known as metamerism. So now you may be wondering, what are polyvalent functional groups? The polyvalent functional groups are namely ether, you can see here this one bond and this one bond, so this is polyvalent. The valency satisfied will be by two alkyl groups, two different alkyl groups: ether, ketones, ester, then 2-degree amine and 3-degree amine, 2-degree amine and 3-degree amine. What is 2-degree amine? This one. So here it has 2 bonds, so polyvalent. 3-degree amine, 3 bonds, so polyvalent. Now for an example, if you want to state an example for metamerism, we'll take the molecule C4H10O. C4H10O. It can be written like this: CH3, CH2O, CH2, CH3. Now the polyvalent functional group here is the ether. This can also be written as CH3O, CH, CH3 and CH3. So the alkyl groups here and here are different. Here it is the ethyl group and here propyl group. So these both are different. Now still it can be written as CH3O, CH, CH2, CH3. Now you'll find that this third one and second one, these both are not metamers, as these two alkyl groups are the same. So the first one and the second one, and first one and the third one, first one and the second one, first one and the third one, these both are metamers. But this second one and third one are not metamers, they are positional isomers, as the position of this group has changed in this if you consider this as the longest chain, the position of this one will be changed. So these both are positional isomers, not metamers. These both are metamers and these both are metamers. Now talking about tautomerism. This tautomerism, it is a special type of functional group isomerism in which two isomers are interconvertible. In all the functional group isomerism, the isomers which are obtained are not interconvertible. But as said, the tautomers are special group isomers, special group of isomerism in which the two isomers which are formed are interconvertible among each other and they exist in equilibrium. So, special type of functional group isomerism in which the two isomers obtained are interconvertible to each other and exist in equilibrium. The two isomers are interconvertible, but how? The tautomers interconvert among each other, interconvert among each other by shifting of hydrogen atom and pi bond between polyvalent atoms, by shifting hydrogen atoms and pi bonds among polyvalent atoms. So we'll start with simple examples and go to complex ones so that every aspect is cleared. So starting from example 1, CH3 CH double bond O. This one, if you shift the hydrogen atom and the double bond, it will become CH2 double bond CHOH. Here what we have done, we have shifted the hydrogen bond here and the hydrogen here and the pi bond over here. So it has, these both are tautomers and are in equilibrium. Similarly, now next example, CH3 C double bond O CH3. This is keto form and this is enol form. So what it is? Keto enol tautomerism. Keto enol tautomerism. Now the third example HCN. This also is a special type of an example. If we interconvert it, it becomes HNC. This is called 1,2 shift diode. So this can be asked specially, is it example for tautomerism or not? So the answer is yes. It is an example for tautomerism. To easily understand whether or not an aldehyde or ketone will show tautomerism, the following conditions should be satisfied by the molecule. So what we are saying, note this, to check if the aldehyde or ketone shows tautomerism, then the following conditions should be satisfied. The conditions are: the alpha carbon after the the alpha carbon is the carbon adjacent to the carbon in which the keto group or aldehyde group is attached. So the alpha carbon should have alpha hydrogen, and it should be sp3 hybridized carbon. To make this note clear, we'll take examples. So we'll start here. First one, H CH double bond O. So here, after this is the carbon in which this is the functional group, okay. To this one there is no alpha carbon, so it does not show tautomerism. Second one, CH3 CH2 CHO. So this is an aldehyde. For this one there is alpha carbon. First point satisfied, there is alpha carbon and it is sp3 hybridized. Why? In the first video of the basics of organic chemistry, we had mentioned to how easily to check whether the carbon is sp3 hybridized or not. So by simply looking at this, it has all the 4 sigma bonds, so it is simply sp3 carbon. So it is a sp3 carbon and it has alpha hydrogen. So this particular aldehyde can show tautomerism. Now coming to the third one, this one here, CHO, this is the aldehyde group and this is the alpha carbon. The first condition, that is the alpha carbon, is satisfied. There is an alpha carbon, but it is sp2. How? From the first video only, it does not have all sigma bonds. It has a pi bond, so it is sp2, and as well it does not have a alpha hydrogen as well, so it does not show tautomerism. Now this fifth example is a special category. Here you'll see this is a keto group. It has a alpha carbon on both the sides. Second condition, sp3 hybridized carbon on one side and sp2 hybridized carbon on the other side. Third condition of alpha hydrogen, there is an alpha hydrogen on this side, there is no alpha hydrogen on this side, as all the four bonds are satisfied. Now it will show this tautomerism on this side but not on this side. So in total, always you should check for both the conditions. So in total this does not show tautomerism. Now in the sixth example, we'll see alpha carbon is there for both of these groups. Alpha hydrogen is there as well, but the carbon is sp2. The alpha carbon in all the cases over here is sp2. Now in the seventh example, there is a special point. If you see this molecule, this is the group, this is the keto group. We want to check about this one. There is alpha carbon on both the sides, alpha carbon. First point satisfied, there is alpha carbon. Second point, about the sp3 configuration is not there, sp2 is there. And the third point, about the alpha hydrogen, there is presence of alpha hydrogen. So we can come to a conclusion that it cannot show tautomerism, but it shows tautomerism. How? Due to extended conjugation. If we learn further about conjugation and all, we'll see due to shifting of bonds, shifting of double bonds, it will show tautomerism. So you may think it may not show, but please remember this particular molecule, this particular structure, it shows tautomerism. Reason being extended conjugation. And the last, eighth one, we'll be taking this example. This one, it has alpha carbon, it has alpha hydrogen as well, and it is sp3 as well. So this will become like this. This one is easier but looks good. We'll take another example here, the ninth example. Ninth example, we'll see CH3, C double bond O, CH2, C double bond O, CH3. This will be interconvertible and it will become CH3COH double bond CH, C double bond O, CH3. So in this one, here it will become OH, it is partially negative, partially positive, and this will be partially negative as it is O. So the electrons in over here will be more towards the O side, towards the O oxygen. It will be partially negative. So there will be attraction in between these. So The next further level of questions, what can be asked about is stability in the tautomers. Which of the tautomers are stable? So on basis of this condition, the partially negative, partially positive, and the attraction between the partially negative and partially positive atoms in the molecule, one can decide about the stability of tautomers. So the questions that can be asked related to this one is, first one, whether or not the molecules show tautomerism, and the second type of questions, the stability of the tautomers. If they show tautomers, which of them are more stable? These two types of questions will be asked. Thank you. Do subscribe, share and comment, and have a look on the description box.